Jai Hind students, how are you all? I hope you are very fine and must be in jovial mood, isn't it? So students, if you are working on something exciting that you really care about, then you don't have to be pushed by some external agency. Actually, your vision itself will pull you towards your dream. So what I mean is actually, if you do that work which you really desire for, then you need not to be motivated or inspired by some external agency. You yourself will get motivated because you love doing that thing. So whatever you do, students, do with your heart. Do with a purpose, right? Don't do it for someone else's advice. Do it for your own satisfaction. The same is in the case of studies as well. So if you are studying, don't feel any pressure. Don't feel any peer pressure. Don't feel any pressure from your parents. You need to study for your own growth. That should be the approach. So students, with that, let's begin today's lecture. We are going to discuss a very, very important concept actually. We are going to discuss the classification of magnetic materials. Faraday classified all the magnetic materials into three categories: diamagnetic substances, paramagnetic substances, and the third one is ferromagnetic substances. So today this lecture is devoted to diamagnetic substances. So we'll discuss diamagnetism in detail. Actually, we'll discuss diamagnetism on the basis of electron theory. Let me introduce this topic. Now look students, every matter, as you are aware, it's made up of atoms and molecules. Now, in the case of diamagnetic substances, each atom possesses paired electrons. All the electrons in the atom of a diamagnetic substance can be assumed to be having equal and opposite orbital motion around the nucleus. So what I mean to say is that, please listen to this particular statement. The motion of all the electrons in an atom of a diamagnetic substance is supposed to be reduced into motion of two electrons because it is having paired electron, and in a pair there are two electrons. One, if it is assumed to be revolving around the nucleus in the clockwise direction, then the other electron of the pair will be revolving around the nucleus in the same orbit in the anti-clockwise direction. So what we will assume is the diamagnetic substance will be supposed or assumed to be reduced into motion of two electrons revolving with same angular velocity, linear velocity in circular paths around the nucleus. Again I repeat students. Each atom of a diamagnetic substance possesses paired electrons, and the electrons in a pair, they have motion, circular motion around the nucleus, but in the opposite direction. Do remember that, right? So again, let me read this statement. The motion of all the electrons in an atom of a dia substance is supposed to be reduced into motion of two electrons revolving with the same angular linear speed in circular paths around the nucleus, right? So let's begin this topic. Let me clarify this point with the help of this diagram, right? So we'll discuss two cases. One is in the absence of external magnetic field. This I have stated very often. In the absence of any external magnetic field, the net magnetic moment of any magnetic substance, be it dia, para or ferro, is always equal to 0. Always remember that. Even if an atom behaves as a magnetic dipole, still in the absence of an external magnetic field, these atomic dipoles are oriented randomly. So the net magnetic moment of a substance is always 0 in the absence of any external magnetic field. Students, it is only when the magnetic substances are brought under the influence of some external magnetic field that it will get magnetized. It will develop its own south and north poles, right? So in the absence, case 2, we'll discuss two cases. Case 1 is when the diamagnetic atom is in the absence of any external magnetic field. Case 2 is when the same diamagnetic atom is under the influence of some external magnetic field. Anyway, let's refer to case 1. As students, we are assuming the diamagnetic substance, the motion of all the electrons to get reduced into motion of 2 electrons revolving around the nucleus in the opposite direction, right? So if one electron is assumed to be moving in the anti-clockwise direction, then the other electron will be assumed to be moving in the clockwise direction around the nucleus in the same orbit with the same angular and linear velocity. Is it clear, students? So this depicts the pair of electrons, right? The 2 electrons forming a pair of an atom in a case of diamagnetic substance. Okay, now coming to this. Here, suppose the radius of the orbit is r, right? And here the electron is assumed to be moving in the anti-clockwise direction. So whenever a body, here the electron follows a curved path, its direction of motion is given by drawing a tangent at that particular point. So this is the velocity vector, which is perpendicular to the radius vector. No doubt regarding this, isn't it? Also students, if it is moving in the anti-clockwise direction, so it will constitute a current in the clockwise direction. So current will be along this direction, in the clockwise direction. So the direction of the current over here would be like this. This will be the direction of the current. Clear, students? Here, the electron is assumed to be revolving in the clockwise direction. So here, the current would be in the anti-clockwise direction, like this. This will be the direction of the current. So here, the direction of the current would be like this. This is the direction of the current at this point. I hope it's pretty clear. Now, I've told you very often a current carrying loop, one face of it behaves as the south pole, the other face of it behaves as the north pole. A current carrying loop behaves as a magnetic dipole. So the face of the loop through which current appears to be flowing in the clockwise direction, that will behave as south pole, while the other face of the current carrying loop through which the current appears to be flowing in the anti-clockwise direction, that will behave as the north pole. And students, the magnetic moment of the current carrying loop is directed from south to north, isn't it? So let's make use of this fact. So here current is in the clockwise direction. So this will definitely act as south polarity. The current is in the clockwise. Current is in the clockwise direction. Here it will constitute a current in the anti-clockwise direction, opposite to that of the electron, revolution of electron. So basically students, this is the current carrying loop and this is where the direction of current is, like this. This is the direction of the current, right? So this face, upper face will act as south, the lower face, bottom face will act as the north. So the direction of the magnetic moment would be like this. This will be the direction of the magnetic moment. Clear, students? In this case, the current is flowing in the anti-clockwise. Since electron is revolving around the nucleus in the clockwise direction, so definitely it will constitute a current in the anti-clockwise direction. So this face, upper face, will act as north, while the lower face will act as the south. So here the magnetic moment is directed from south to north. So upper will act as north, the lower will act as south. So here the direction of the magnetic moment would be like this. Clear, students? Also remember, in the previous lecture we have discussed the magnetic moment associated with the revolution of an electron around the nucleus. It's given by EVR divided by 2. So, in both the cases, E is same, orbital velocity that remains same in both the cases. It is orbiting in the same orbit, same radius. So, magnitude of M is constant. We are discussing case 1 when there is no external magnetic field. So now look, students, these two magnetic moments, due to the due to the revolution of the electrons around the nucleus are equal in magnitude and oppositely directed, and thus obviously they tend to cancel out or nullify the effect of each other. Therefore students, net magnetic moment of each atom of a diamagnetic substance is always 0. Clear? So therefore, net magnetic moment would be equal to, if this is taken as positive direction, whatever, n plus minus n. So it will be equal to 0. Both are oppositely directed, so they naturally will tend to cancel out the effect of each other. Clear? So net magnetic moment, it would be equal to 0. So in the absence of external magnetic field, each atom of a diamagnetic substance possesses 0 magnetic moment. Clear students? It is for case 1 when the external magnetic field is absent. Understood? Now what to do is, let's consider the second scenario. Now we will consider the same atom of the diamagnetic substance to be under the influence of this external magnetic field directed upwards. This is under the influence of external magnetic field directed upwards. It's the same diagram. This is in the case of absence of magnetic field, and this is the corresponding diagram in the presence of magnetic field. Suppose let's consider it to be 2 dash. Okay, we are dealing with the same case. So here the electron is assumed to be moving around the nucleus in the anti-clockwise direction. So its directional motion will be along this direction only. So it will constitute a current in the opposite direction. Same. So here this is the radius, and this electron will be under the influence of this magnetic field directed upwards like this. This is the direction of the magnetic field. So students, now listen, very very interesting article. So this is current, since the electron is revolving in the anti-clockwise direction. So it will constitute a current in the clockwise direction, right? This is the same case as this one. The only difference is that this was in the absence of magnetic field, this is in the presence or under the influence of magnetic field. So the same electron will be under the influence of magnetic field, right? So this electron under the influence of magnetic field will experience magnetic force. So the angle between this magnetic field and this current is 90 degree. So we can make use of Fleming's left hand rule so as to determine the direction of the magnetic force, isn't it? So let's try to find out the direction of the magnetic force then. FBI, you remember students? This is force, this is magnetic field, and this is current. So like this, magnetic field, it's directed upwards. The central finger represents the direction of the current. Since the electron is assumed to be moving around the nucleus in the anti-clockwise direction, so current will be in the clockwise direction. So current would be in the outward direction, which has been indicated by this central finger. So what about the magnetic force experienced by the electron then? It will be directed radially inwards, isn't it? So it will experience a magnetic force along this direction. Obviously, all are mutually perpendicular to each other. Clear students? So what happens is, let's consider case 2. And in the first case, in this case, the magnetic force acts radially inwards. FM, magnetic force, acts radially inwards. So what happens is, the net centripetal force will increase. Now as we are aware, the very basic fact, electron revolves around the positively charged nucleus because the electric force of attraction between the negatively charged electron and the positively charged nucleus provides the electron the necessary centripetal force, isn't it? So here, the centripetal force was only due to the electric force of attraction between the electron and the positively charged nucleus. But here, this force will also add up. So here in this case, the net centripetal force which acts in the radially inward direction would be equal to Fc vector plus Fm vector. Since both are in the same direction, so it will get added up. So in magnitude, it can be simply written as Fc plus Fm. So as a result, students, net centripetal force increases. I think it's very, very clear. Again, I repeat, students, since the revolution of electron around the nucleus in the anti-clockwise direction will constitute a current in the clockwise direction. So by applying Fleming's left-hand rule, we have obtained that this electron will experience a magnetic force in the radially inward direction. It is revolving, so it must be acted upon by some force, which is the electric force. So these two forces will add up. That is, these two forces will add up because of the fact that they are all together being directed in the radially inward direction. So both will contribute towards the net centripetal force. As a result, the net centripetal force increases. Now students, centripetal force, we are aware, it is given by mv square by r. We all are aware. Net centripetal force is given by mv square by r. So if the net centripetal force increases, it means that it will result in an increase in the magnitude of the orbital velocity of the electron. Why? Because mass of the electron will remain the same. The electron will keep revolving in the circular orbit of the same radius. So with the increase in the centripetal force, it suggests that the magnitude of velocity of the electron with which it is orbiting around the nucleus will definitely increase. So if earlier it was revolving around the nucleus in this orbit with velocity v, now it will have orbital velocity slightly greater than this. So it may be considered to be v plus del v. Clear, students? So it has slightly increased. So that is why the arrow indicating the velocity v plus del v is shown to be somewhat greater than the arrow indicating v. Understood? So it tends to, now under the influence of this external magnetic field, the electron tends to revolve around the nucleus with larger orbital velocity. So its velocity increases. Now what happens is, with the increase in the velocity, the magnetic moment also increases because rest of the terms are constant. E is constant, the electron revolving in the circular orbit of the same radius, 2 is constant. So with the slight increase in the orbital velocity of the electron around the nucleus, the magnetic moment constituted due to the revolution of the electron around the nucleus also slightly increases. So if earlier due to this revolution of the electron the magnetic moment was m, now it would be slightly large. If earlier it was m, now it will be m plus del m. Let us consider the magnitude to be m plus del m. So the length of the arrow is slightly greater than this one. And direction it will be same as was in this case. Clear, students? I hope you have understood this concept. Let me try again to convince you, right? What I have stated is these two are the same diagrams of the same electron. But in first case it is in the absence of any external magnetic field. In this case it is under the influence of this external magnetic field directed upwards. As the electron comes under the influence of this magnetic field, it will experience a magnetic force, and this magnetic force is directed radially inwards. So obviously it will add up to the net centripetal force. So as a result, the net centripetal force increases. Now as the centripetal force is mv square by r, m and r is constant, therefore increasing the centripetal force clearly suggests that the magnitude of the orbital velocity of the electron must also increase. We have assumed it increases from v to v plus del v. Clear? Now m is EVR by 2. So with the increase in the magnitude of the orbital velocity, the magnetic moment due to the revolution of the electron around the nucleus will also slightly increase. So if earlier it was m, now it is m plus del m. I hope now you have understood completely. Right? Okay. This is over. First dash, it is over. Now let's consider this case. Second case and second dash. Okay. In this case, we have assumed pair of electrons having opposite orbital motion. So in this case, if we have considered the electron to be moving in the anti-clockwise direction, here the electron will be assumed to be moving in the clockwise direction. Its velocity vector would be like this. So it will constitute a current in the opposite direction. This is the direction of the current. Clear? So here the current is in the anti-clockwise direction. So it is under the influence of this external magnetic field. The angle is 90 degree obviously. The angle between the current and the magnetic field is 90 degree. So here the electron under the influence of this magnetic field again will experience a magnetic force. So if the direction of the current and magnetic field is given and it's 90 degree, then we can very much make use of Fleming's left hand rule so as to find out the direction of magnetic force. This is F, this is B, this is I, right? So let's check it out. This is B. Current is in inward direction, right? It's in the clockwise direction. This is magnetic field. This is the current in the inward direction, clockwise. So it will be in the inward direction. This is force. It's directed in the radially outward direction, right? So this is the magnetic force it will experience. This is the magnetic force. All are mutually perpendicular to each other. All are mutually perpendicular to each other. So got the difference now? Here the electron was experiencing magnetic force in the radial inward direction. Here the electron, the other electron of the same pair will experience magnetic force in the outward direction. Now centripetal force already, it always acts in the radial inward direction. And centripetal force, as I have stated, it's provided by the electric force of attraction between the negatively charged electron and the positively charged nucleus. Now these two are of opposing nature. So what happens? In this case, Fm, the magnetic force, let me write this statement first, Fm acts radially outwards. So as a result, net centripetal force acting on the electron, it will be given by Fc minus Fm. That is, net centripetal force decreases. I hope it's very much clear. Here, both were in the same direction, radially inward. Here, both are in the opposite direction. So, magnetic force experienced by the revolving electron, it opposes the centripetal force. So, the net centripetal force decreases, right? Now, net centripetal force decreases. Now, net centripetal force is mv square by r. So, with the decrease in the net centripetal force, the orbital velocity of the electron will also decrease, say from v to v minus dv or v minus del v. So since centripetal force is mv square by r, and as I told you, mass of the electron and the radius of the orbit will remain constant, the electron will keep revolving around the circular orbit of the same radius, isn't it? So with the decrease in the net centripetal force, the orbital velocity of the orbiting electron will also decrease, say from v to v minus del v. So earlier if the velocity was v, now it will be v minus del v. Am I clear? So I've indicated this velocity with an arrow of smaller length, right? Okay. Now with the decrease, now we are aware F is equal to EVR by 2, isn't it? Now with the decrease in velocity, the magnetic moment will also decrease. The rest of the term remains constant. So with the decrease in the magnitude of the orbital velocity of the electron, the magnetic moment constituted due to the orbiting electron around the nucleus will also get decreased, say from m to m minus del m. So earlier if it was m, now it would be m minus del m. The arrow must be smaller as compared to this one, right? It must be smaller, it must be somewhat smaller. So I hope you have understood the concept, students. Now look what happens. Under the influence of external magnetic field, these are the magnetic moments. Both are opposite directed. M plus del m, it's directed perpendicular to the plane and downwards, isn't it? M minus del m is directed perpendicular to the plane and in the upward direction. No doubt both are oppositely directed. But the most important point to be noted is that both are of different magnitude. So they won't cancel out the effect of each other. it will acquire net magnetic moment. So, net magnetic moment acquired by the diamagnetic atom under the influence of external magnetic field would be given by let me write the expression over here. So, under the influence of under the influence of external magnetic field, the net magnetic moment, it will be given by, this one is dominating one. So make use of the laws of vector addition, they are opposite directed. So in magnitude, the resultant will be given by the difference in the magnitude of these two moments. So it will be m plus del m minus m minus del m. So that will give us, so the net magnetic moment, it will be equal to del m minus s plus del m. So it will be twice del m. So definitely the diamagnetic atom under the influence of this external magnetic field will develop some magnetic moment, which is twice del m, very small magnetic moment, and in a direction opposite to that of the external field. Here external field is assumed to be directed in the upward direction. So resultant magnetic moment would be in the downward direction. Isn't it? This one is dominating one. M plus del m is greater than m minus del m. So as per the vector algebra, resultant would be given by m plus del m minus m minus del m along the direction of m plus del m. Clear? So students, ultimately what we have concluded is a diamagnetic, a dia substance, you can write a dia substance or a diamagnetic atom, or you can generalize it, you can write it as a substance, get feebly, that is weakly magnetized. This we have proved. And in a direction opposite to that of the applied field, applied magnetic field. This is a very, very important point which we have proved. Right? This is the ultimate conclusion. So students, in the absence of any external magnetic field, the net magnetic moment of each diamagnetic atom is zero. But when it is under the influence of some external field, then the atom get magnetized, it get feebly magnetized, and in a direction opposite to that of the applied field. It is getting magnetized in a direction opposite to that of the applied field. Right? So that's the conclusion. So let me summarize the entire thing. First point. In a diamagnetic substance, every atom possesses paired electrons. Second point, the motion of all the electrons in an atom of dia substance is supposed to be reduced into motion of two electrons revolving with same angular velocity in circular paths around the nucleus. That is what we have considered. And in the absence of external magnetic field, the net magnetic moment being equal in magnitude and opposite directed get cancelled out. So in the absence of an external magnetic field, net magnetic moment of each atom is zero. When it is under the influence of external magnetic field, then what happens? Then they are oppositely directed but of different magnitude. So each atom acquires some net magnetism. It gets feebly magnetized. As a whole, we can conclude that, or we can generalize that a diamagnetic substance under the influence of external magnetic field get feebly, weakly magnetized and in a direction opposite to that of the external applied magnetic field. Clear, students? And there are various examples of diamagnetic substances: bismuth, zinc, copper, gold, silver, water,